So let's try to understand a bit about log-log plots, why we use them, and what they even mean when we try to plot the log error up against, for example, the log of some step size. Let me see here. Okay, so let's just assume that we have some idea that the error when we use some finite difference scheme to approximate a solution to a differential equation, let's just assume that we have an idea that this error has around the same order of magnitude as, for example, h squared. Well, what does this mean intuitively? Intuitively, this tells us that the error as a function of h, the step size, is more or less the same as some constant c multiplied by h squared for h small enough, which means for as long as the step sizes are close enough to 0. And of course we assume that c is greater than equal to 0 here. Now if I take the log on both sides of this, then what we can observe is that the log of the error is then approximately equal to some constant log c, now I'm just using logarithmic rules here, plus log of h squared, which is the same as plus 2 times log of h. And from this we can see that the logarithm of the error as a function of h is actually, so the logarithm of the error is a linear function of the logarithm of the step size. And which slope does this linear function have? Well, you've probably guessed it already, it has slope 2. So consequently, this means that if somebody gives me a plot where they say, well, here I have the log of the error, and here I have the log of the step size, and it looks something like this, and you observe that for each unit you go along this axis, the slope is q. Then this means that we can infer that the error is approximately the same order of magnitude as h to the q, in the sense that as h decreases towards 0, then the error will also shrink and become smaller and smaller in more or less the same way as h to the q, which also means that if you have two log-log plots, two graphs in a log-log plot, and one looks like this, so it has a much more steep slope than another one, then what you can conclude is that the method that gives you this error plot over here gives you an error, let's just say that this slope is p, gives you an error that has the order of magnitude h to the p, where p is greater than q. And which method would you then prefer to use? Well, the rule is choose the one with the steeper slope, because this means that as log h goes in this direction, aka as the step size decreases, this graph will decrease more than this one. And that's a good thing, because that means that then we'll have a log error that's smaller. Now, normally this, Sorry. Now, normally this method here is not exactly the best way to illustrate how the error changes as the step size changes, just because of the mere fact that we're interested in what happens when h decreases towards 0. So we're interested in what happens when we move in this direction. So we're interested in what happens when we move in the decreasing direction. However, the y-axis goes in this direction, and just very intuitively, the way we interpret graphs and their slopes, etc., is always in this direction of the y-axis. So there are two ways that we can circumvent this. We can instead consider plotting the negative value of log step size along the x-axis, and then plot log error along the y-axis up here, which would then give us graphs that go downwards this way. And that's of course very nice. And then if I read the slope that's minus q, then that means that the error has the same order of magnitude as, well, h to the q. Now, another thing that's done quite a lot in literature is to plot the log error up against the logarithm of the number of time points that we use in our finite difference method. And why is that? Well, recall that m is equal to t divided by k, where t is the length of the interval that we are calculating, that we're doing our calculations on. And this actually means that if I take the logarithm of m, then I get some constant log t minus the, let's just write h as step size so that we use the same symbol all the way through, minus log of h. And what this means is that here I will get in the blue graph, I actually get the same kind of line as the purple graph. It's just translated by log t. So it will probably look something like, well, that depends completely on the value of t, but it might look something like this. And this slope will also be minus q if this slope up here is minus q. And when we read a slope like this, yes, that means that the error is big O of h to the q. So it has the same order of magnitude as h to the q, and it behaves in the same way as h to the q as h decreases towards 0. Now, before I finish this off, there is one last thing that I think probably we should talk a little bit about, because now I've been repeatedly saying, let's plot the log of the error along the y-axis, and I keep talking about the error as a function of the step size or of the number of time points we calculated. But one thing that's actually really important to understand is we haven't really defined what we mean by the word error. So let's try to define that. What do we mean by error? Well, let's just say that I have some differential equation and I've managed to solve that differential equation, and I've managed to plot the exact solution of that differential equation in some coordinate system here. So let's just say that this is the exact solution of my differential equation, and I will call it y. let's just say I have t along the time axis, so this is y of t. And let's also assume that I've used some finite difference method and discretized my time axis on an interval 0 to t into smaller intervals that each have the length k. And let's just say that my approximated solution looks something like this. Well, I don't know how it's supposed to look, but let's just say it looks something like this. Then what would we normally mean by error? Well, by error we mean some kind of deviation or difference there is between my approximated solution, that I would choose to call y bar here, and my exact solution. So error would have something to do with what happens in these points here, which difference that I can evaluate between my exact solution and my approximated solution. But there are, all in all, m of these points. So it's not just a question of saying, let's talk about error in general. It's actually more a question about thinking about how should we evaluate the total of these different errors in these different time points. So there are some different ways that we can choose to summarize what the error is for some given finite difference method that we use with a given step size k. And one way we can do that is to say, well, let's take the biggest of these differences that we can find. So if I call this error epsilon 1, epsilon 2, epsilon 3, and so on, up to the last one, which is epsilon m, then we say define error as the maximum of these epsilons, where each of them is equal to the absolute value and difference between the approximate and the exact solution. And another way we can do this is probably to say, well, let's define the error as the average of these epsilons. And the third way we could probably do this is to say, let's define the error as, well, let's just define it as the last one that we observe here, because in some way, since I have been doing Taylor approximations all the way up to time point t, and I've been doing this for m time points, then maybe epsilon m is some kind of worst case scenario that I can achieve. So there are different ways that you can try to sum up the error of some finite difference method when using some given step size. And to be honest, all of these are seen in literature and there is no specific correct answer. Sometimes one will give you one result, another will give you another, and depending completely on which method you're using, the reason for those different results could be one for one method and another for another method. But now you know that there are these three different ways of doing it, and you understand how to look at a log-log plot and interpret the slope, and also why we use these log-log plots to visualize how different types of error when constructing, when doing finite different methods, well, how these different types of error, they change as we change the step size or the number of time points we use.